Hey, Professor.
Yeah, hi. Hi, Ariel.
How's it going? I still don't have access to Gradescope, so I wasn't sure how to get on there.
Hmm.
Yeah, same here.
Yeah, my problem is when it's just like supposed to be hooked in with the class, and I don't see what's going on in it once I put something in. So what I'll do, guys, I'll put this announcement before I send this out, but I'll send another kind of a fake thing
Okay.
through like tomorrow, and just let me know if you don't get it. And then it's not a big deal if you don't have access to it, because I can always take your tests and stuff from email and plug it in. So, but it'd be nice to figure out. I think it'd be a nicer flow. So I'll do that,
Okay.
and see if we can flush out what the problem is.
I was wondering, are the homework assignments posted on Gradescope?
No, they're actually on. They are on the Blackboard,
Oh, okay.
and there's no grade associated with the homeworks. They're just for practice,
Yeah, okay.
and the solutions are also on the Blackboard. I think they're just at the very like the top level. They're not part of any module, I don't think.
Okay. Um, let's see. Because I've gone through home, start here, course information, course document, or course content,
Yeah,
and I don't see them in there. I was able to get the first homeworks from another classmate because I thought they were on Grayscope,
yeah.
but I'm not sure.
Let me take a look. I was hoping they were on there. Um, Give me one
They were
second.
supposed to be in the course schedule, right? Yeah,
Boy,
the course schedule.
let me get in there
Yeah,
and
it's
see.
under the course schedule, and you
But
have
I
to
think
change it to a doc like file.
Oh,
it's only for the first module, which, well, just chapter 2. There's nothing from like 3 and so on.
Yeah. Do you guys see the course content? Do you guys see the solutions to the homework? Arielette, do you see it? It should be in
uh,
the content, course
course.
content. So if you scroll down the course content, not part of any module.
Oh, yeah, I see the solutions.
Yeah. And like the guys were saying, the actual, like the call out for what the problems are, I put the first module in the course schedule.
Okay.
And then I got an update for basically the second set of homeworks, I guess, which I
Okay.
haven't done yet.
Sounds good. Thank you.
Okay. Let's see. Just one second, guys. Let me get myself going here. Um, okay. So today we're going to do, I think we're just going to end up doing pretty much a whole bunch of examples. And to, sort of like these tricky circuit analysis is kind of starting. It's a tricky, I think it's, well, it is, some of it is tricky, I gotta say. Okay, so let's see where we were last time. So last time, we were also doing some examples towards the end. And was there any questions about what we've done in the last lecture, last few lectures? Anything you guys want me to go over that's not clear?
I guess I just wanted to see a couple of the circuits with diodes, but we'll get in there.
You mean the new examples, kind of, or
yeah.
Okay, I got you. Okay, so sorry guys, just give me one more second. Let's see. Okay, so so I think where we left off last time is what happens in the case when we have a battery connected across an ideal diode. So let me just redraw this thing again. So we had this, real diode. Just go from the beginning. So that had this characteristics of, if we plotted VD, if we took the diode and put it in circuit like this with VD and this being I sub D, we ended up with this exponential characteristics when VD is positive, when basically when this node is higher than this node, you had this exponential characteristics that look like I sub D is equal to I sub S exponential of VD over V sub T. Okay, so the full equation was this -1, but because very quickly this gets much, as you move over here, very quickly this exponential, because it's an exponential. Let me say a couple more things. So VT is KT over Q. Okay, sorry guys, this is like you've seen this over, and I'm just gonna keep saying it over and over again because a few things I've memorized is these things. And then at room temp, at T equal to 300 degrees Kelvin, or room temperature, or otherwise known as room temperature, V sub T is approximately equal to 26 millivolts. Okay, so V sub T is a constant and it's a pretty small number. So again, if you're like just at V sub D of, I don't know, like 260 millivolts, you have an exponential to the power of 10 here. That's much, much bigger than 1. So for all purposes, we can just, when we're in this region, when V sub D is, when we're going in this direction, we just say I sub D is approximately, we just get rid of this 1. So it's approximately I sub S exponential of VD over VT out here very quickly. Okay, so that's the equation we pretty much need to remember there. And then, by the way, I sub S depends on is diode dependent. It depends on the doping concentrations and et cetera, but it's kind of, it'll be given to you either in a spec sheet for a real diode, or in this class, it'll be like giving you the problem, but it's a pretty small number. I don't know, one sort of, that'd be a pretty big one to 1 times 10 to the minus 16th amps. So like a really, really small number is I sub s. Okay. And then so this is called forward bias. This region is called forward bias. Okay. And then as you go negative, we still had the same equation, okay? But here, because the exponential becomes very, very small, so here I have the same equation. ID is equal to I sub s exponential of VD over VT minus 1. Now we have the same thing happening on this side. So this is the complete equation, okay, again, on both sides. But where the approximations happen is here when VD is a negative number, this exponential quickly becomes very, very small. So this exponential becomes close to, is like much, much less than 1 very quickly out here, as soon as you get very little by. So then this thing, I sub d, turns approximately into minus I sub s. So you end up here, you end up with I sub s, okay, minus I sub s essentially. Okay, but again, it's the same equation. So whether it's forward bias or reverse bias, so this region is called reverse bias. It's the same equation, which is this guy, but because of this exponential characteristic of the relationship of ID with VD, very quickly you can either just get rid of the 1 and stay with an exponential, or end up at minus I sub s. But you end up with this characteristics for your diode. Okay, so this is called, I don't know what this is called. This is just a diode. Let's call it a diode for now. Or let's call it exponential model.
And this is more of the real one, right?
This is close to being the real one. Yeah. So so we call this the exponential model. This is as close to a real one as you're going to get in hand calculation. I mean, the real one, you know, has got third order effects, fourth order effects, whatever. But this is for us, this is real. So this is the real model. And unless you're going to go, I don't know, you're going to go and build diodes in a semiconductor fab, this will be as real as it'll ever be, even if you're designing circuits for a living. Like I never go any deeper than this. There's like different things happens in this exponential, but it's all sort of third order effects. Okay, so this is the exponential model. And then we introduced this thing called an ideal model. And we said, hey, it would be neat if we had this thing called a diode, and it would, it's the same circuit. Same circuit, except this time it's like we took this curve, and really dumbed it down. And we said, okay, let's just pretend like the diode turns on. And so, sorry, VD and I sub D. So it's the same curve, same thing. Except again, I'm really dumbing it down. I'm redrawing instead of having an exponential curve, here I'm just saying it's like the resistance is 0 here. So if VD is greater than 0, greater to equal to 0, R sub D is equal to 0. Okay, which means I'll say what it means here. And then out here, when VD is less than 0, R sub D is equal to infinite. Okay, so what we did again is, so what does R sub D equal to infinite does? Or let's say R sub D was just a very, very big number, right? Then we'd end up with in this region, we'd end up with a very, very big resistor. So this would equal to a resistance. R sub D would be, I don't know, let's say 1 times 10 to the 20th, say. And you'd end up with a very little current here. Okay, it'd have a slope, but it'd be such a small current that like, it'd be a small current. So we just called it infinite to make our life easy. So it's basically like the first order approximation of this really, really small number. Oops, sorry guys. This really, really small approximation of this really small current going back. Okay, and on this plus side, we just said the diode turns on and R sub D goes to 0 and you get a huge current going through. So let's just redraw this thing. So if VD is less than 0, your circuit ends up looking like an open switch. That's what we're modeling the diode. So that's what it would look like. Okay. So again, in this case, R sub diode is equal to infinite. There's no connection here. If there was a resistor, it'd be an infinite resistor. It'd be no current flowing. And then a VD is greater than or equal to 0, then R sub D would be 0, which means that you'd have a closed switch with 0 resistance. And basically, you just, as soon as VD just gets a little bit, so remember I sub D is V sub D over R in this circuit. So if I make this thing 0, as soon as VD goes even a little bit positive, the current goes to infinity. Okay, so that's what it looks like. So this is the ideal model, and we're just really dumbing down this complicated model to analyze, to make circuit analysis easy. Okay, and so that's one tool we could use. And we'll see when we can use that, when we can't, when we should use it, when we shouldn't. So that's the ideal model. And then there's a third model that goes to, which does a little bit more improved version than this. Okay, so this is called the constant voltage model. Sorry guys, can't seem to turn that off. So what we do with the constant voltage model is we decide we're a little bit unhappy about this region here. Okay, right over here. So while it's true that this current really takes off here, it kind of takes off a little further in than right at 0. Okay, so it probably takes, I mean, it's going up, but so we think what if we shifted this thing over some, and that's the constant voltage model. So what that looks like is if I plot it again with the same circuit, just a different model. I'm just gonna VD and I sub D. I'm just gonna push over the point at which the diode turns on, that crossover point, over to a place called VD on. Okay, and this is the so-called constant voltage. And you know, for the purposes of this class and tests and so on, you'll be given this constant voltage, but it's, you know, usually ends up, the assumption is usually that's around 1 or equal to 1 volt. And again, we're trying to basically model something that, I don't know, does this, with this being a really small value. Okay, so the way this thing works is now when VD is greater than or equal to VD on, R sub D is equal to 0. So we just move the point where that happens. And when VD is less than VD on, R sub D is equal to infinity. Okay, so again, if I redraw this guy, it's gonna end up looking like, so when VD is less than VD on, this switch is open, okay? And because we have this situation where we're shoving this over by 1 volt, okay, what we do is, instead of, remember in the case of the ideal diode here, we modeled a diode. Let's just draw it the other way, so as not to confuse you guys. We just modeled a diode as a switch that's either closed in this case or open in this case. Okay, so that's the ideal model. In the case of the constant voltage model, we are modeling the diode as, so the diode looks like two things. It still looks like a switch that's closed, say, but we're putting a voltage of VD on in series with it to get this effect. So this is a symbol for a battery, drawn very badly, just kind of looks like that. Okay, so we're putting a battery of value of VD on in series with the diode when it's on, and when it's off, the battery is still there, but it really doesn't matter because the switch is still off, and you don't, anything looking down on this thing doesn't really see it. So V off, V on. So if I redraw the circuit, when the VD is less than VD on, the circuit, I get this thing. And then when VD is greater or equal to VD on, I get a short here with the battery in series. Okay, which has the effect of, this is just like a fake way of getting me to this curve, or whatever you want to take it. Just again, these are models to help us get. So what we want to do is, if you guys that did the homework, you noticed how quickly when we had a exponential thing in a circuit, when we're doing hand calculations, things got really complicated. We had to do these multiple iterations to converge to a number and all that stuff. We want to, this is all an attempt to get rid of that exponential thing in our equations. And we just want just a simple on-off thing. The price we pay for that is that we have to make this decision ourselves. Okay, this decision between whether the diode is on or off, we have to do it ourselves. So I don't know how you want to look at it, sort of like we went from sort of an analog thing with just throwing everything in there and calculating exponentials and doing iterations to a digital approach where we are the gate or whatever deciding whether the diodes in the circuit are on or off and which model to use. Okay. And so sometimes, and so again, in the context of this class, when you get a problem or a quiz or whatever, you'll be told whether you should be using the constant voltage model or the ideal diode model. And then sometimes you have to, and then there is a possibility, there's a third possibility that you might actually have to revert to this exponential model. And we'll see when that is. And again, you might be told you need to do that, or you might just have to figure it out yourself, that there's something that these models don't include. And the primary thing that these models don't include, if you guys remember back a couple of lectures ago, we talked about how IS1, I sub S, which again is this number, I sub S, that's dependent on the area of the diode. Okay. And since this IS is, multiplying by this exponential, it can be an important thing. So let's say we're going to look at this example. So we're going to look at this example where you have a resistor. We'll look at it later on in the lecture. Hopefully we'll get to it. I think it's something like this, where you have two diodes in parallel. Okay, it's a circuit like this. And the area of D1 is unequal to the area of D2. And now, you can't, and basically what that means is, a different current is going to go through D1 that it is through D2, which means that ID1 is unequal to ID2. So you can't use the ideal model or the constant voltage model to analyze the circuit, because both of those will claim that ID1 is exactly equal to ID2, whether it's infinite or whether it's zero. They'll say it's exactly the same. But because of, if their areas are not the same, we know they can't be the same. So like in a case like this, we'll see you have to go back all the way back to an exponential model. Okay, so, and just to sort of one little last bit of house cleaning, I forgot who it was that asked last lecture about in the case of the ideal model, what happens exactly at VD equal to 0? And basically at VD is equal to 0, we're saying that I sub D, the switch is on. So we're actually saying when VD is greater than or equal to 0, the switch is on, okay? But right at VD equal to 0, although the switch is on, the voltage across of it is 0. So I sub D is 0. Exactly at VD equal to 0, I sub D is actually 0. But as soon as you go to any, VD is 1 times 10 to the minus 20, or sorry, yeah, 1 times 10 to the minus 20, or a real small number, the I sub D pegs. Okay, it goes to infinite. And the same thing is true here. So you have to make sure you consider that its VD is, the diode is on when it's at 0 or at VD on, depending on ideal model or constant voltage model. Okay, so let's see if that's anything else I want to say about that. Okay, so any questions about those models? So we have 3 models, and 2 of them are just to make life, like make circuit analysis easy, the ideal and the constant voltage. But at some point you can't use either one. Again, most of it typically has to do with this area or something like that. And then you have to revert to the exponential model. Okay. All right, so now let's start doing some examples. Let's see. Okay. All right, so the first one, and these are examples are in the book, and I think also in the lecture notes. So the first one, we were going to go through example 3.12. 3.12 from the book. And here our model is still an ideal model. So assume ideal diode model. And this is what the circuit looks like. We have a resistor R1, R2, and then we have a diode. And we've been asked to look at the voltage in versus voltage out graph. Okay. So a couple of comments here. One is always make sure you guys are answering the right question. So usually what that means in this class is we have kind of probably, by the end, we'll only really have 3 types of graphs, I think. One of them is V in versus V out. The other one is VD versus I sub D, or V over V and I. And then sometimes you have V or I, usually V, with respect to time. Okay, but anyway, for this problem, they just ask us to do V out over V in. Okay, so, and then the other observation is even like a really simple circuit like this, I personally couldn't come up by like looking at it, what this curve looks like. And this is like as simple as it gets, 2 resistors and a diode. So that's why we sort of have to get used to this analysis method. So the methodology, first one we use is we assume we look at 2 cases. One of them is V in being very negative, and then what happens. And then we look at the case for V in being very positive, and then we see what happens. Okay, that kind of helps us with the analysis, because at the extremes of V in being minus infinite or plus infinity, sort of easier to get our heads around the problem. And then, but pretty soon, even like maybe here, we'll have to figure out where the break even is, where do things change from negative to positive. But let's start looking at it. So first, let's assume V in is very negative. So let's say it's minus infinite or something. Okay, so what happens? If V in, oops, if V in is very negative, so this guy is very low, okay, this point of the diode, the P side is gonna, regardless of the resistive drops or whatever we got here, this thing, remember we're saying it's at minus infinity. So we're just forcing essentially this point to be lower than ground. Okay, we're just forcing that to be the case. And we know if this guy is lower than ground, then in the case of an ideal diode, okay, which is the assumption here, then I'm going to call this D1. Then D1 is off, meaning that I can redraw D1 in my circuit as an open switch. Okay, so the next observation here, guys, is I recommend, and I keep getting burned because I'm a lazy person, to redraw the circuits once you make a decision. Just redraw the circuit. Sooner or later, you're going to get into trouble if you don't. So basically, we have this R1, B in, B out. Okay. And then let's say Vn is, so that's what it looks like. Okay. So let me see if I can draw the equation for this. So here, it kind of looks like a resistive driver with that divider between V out and Vn, but notice this is open. So this R is just floating. So it really has no effect. Okay, so just V out here, in this case, when Vn is minus infinite, V out is just equal to Vn. Okay. And then Vn is positive infinity. Okay. So again, we're forcing this to be very, very high. So I'm forcing this node to be higher than ground. Whatever it takes, I'm just forcing it to be higher than ground. Then D1 is on. D1 is on. And I want to redraw D1 as a closed switch. Okay, and let's redraw the circuit again. This time I'm going to draw D1 as a closed switch.
It becomes a voltage divider, right?
Yeah, it just looks like a voltage divider then. So here, V out is equal to R2 over R1 plus R2. Yeah. Okay, so if I was going to draw this, okay, when V out is negative, so here.
Is it times V in?
I'm sorry?
Or V out? Is it times V in or V out?
Oh, I'm sorry. Yeah, it's times Vn. Thank you. Thanks, Epsilon.
Sure.
Okay, so when you're negative, you're out here. And so V out here, V out is just equal to Vn. I was going to draw that. V out is equal to Vn. And this is where, sometimes we go wrong. Remember, Vn here is negative. So V out also has to be negative. So, sometimes you get the tendency to draw it like this. But remember, V out is equal to Vn. So just follow the equation and you'll be okay. So it'll go negative. And this slope is just slope of 1. Okay, because V out is equal to Vn. That's the equation there. Okay, here, out here, V out is R2 over R1 plus R2 Vn, which means that your slope will change to R2 over R1 plus R2. And again, because Vn is positive here, V out is also going to be positive. Okay, so that's the solution there. You're going to have a two lines, so two linear curves with two different slopes depending on whether Vn is negative or Vn is positive. Any question about that? Okay, so let's go. So that was one example. Let's go to the next one. Okay, so maybe it's the same example. So, and now, so we have the same circuit, except this one we assume a constant voltage model. So again, here we solve this with the ideal, diode model. And now we're going to solve the same thing. So the same circuit. With the, so now assume constant, bleh. And then redraw V out over as a function of Vn. Okay, so we do the same thing, same analysis. So first assume Vn is negative. Sorry, is okay. So again, we're forcing this node to be lower than ground, meaning that we're turning off VD. So D1 is again off. And we draw D1 as a switch that's open. It has a battery in series with it with VD on, but it doesn't matter because you won't see the battery because the switch is open. So if I redraw the circuit, it's like an open switch with this battery in there. Okay, so again, V out is equal to Vn in this case. Okay, so then when Vn is positive infinity, D1 is on. So again, we're basically forcing this node to be very large. Okay, meaning that we're forcibly turning on D1. D1. So we'd redraw it as a closed switch now with a battery across it. And now that battery does matter. Okay, so if I redraw the circuit again, so what Viad looks like in this case is it still looks like V Vn times R2 over R1 plus R2, but plus Vd on. Okay. So let's look at what happens in this curve. So here, I think it's kind of easier to draw the positive one first. So when no, I screwed this up. Sorry, guys. Oops. Oh, let me see. No, that's correct. I think that's correct. Okay, so now what happens is it looks like we ended up with the same curve, okay, but we moved the breakpoint over. So remember the breakpoint here was when Vn was equal to 0. Okay, now we move the breakpoint to when Vn is Vd on. And that's when we get a break. So here, this ratio is, the slope is 1. Here, the slope is R2 over R1 plus R2. But we basically made this breakpoint when Vn is equal to Vd on. Okay. Any questions about that, guys? Noticed something interesting happened that, again, sometimes people get wrong. We shifted, things got shifted over, okay, but they kind of shifted VD on as well, right? So it didn't do this. So just sort of be careful with that. Okay. Okay, let's keep going here. So let's do another example. And this one. Okay, and for this one, so I don't know what we want to call this. I don't think this, I'm not sure this was in the book or not, so I want to call that example X. I don't know.
It's 3.14.
3.14, thank you. Okay, for this one, assume constant voltage model as well. Okay, so again, first we assume and then we want to get V in versus V out. Hey, why don't you guys actually try to give this thing a crack, actually, instead of me doing it? Why don't I give you a few minutes to give it a try? So again, what you want to do is first, you look at when Vn is minus infinity, And then the second case when V in is equal to positive infinity. This one's a little bit more tricky because you have to actually try to figure out where the cross point is. Okay, so give that a shot with a few minutes.
When we have a constant voltage model, the battery is always in series with the diode, right?
Yes.
Thank you.
So it always looks like the diode, oops, yeah. The diode, so it always looks like a switch. Now, whether it's on or off, like that, or like that. Okay, guys, let's look at it together. So the first thing you guys should have all done, again, is look at where the case for Vn is very low, so minus infinity, in the case where Vn is very high. Okay, so where Vn is very low, we're basically forcing this node, this P side of the diode, to be much lower than ground. Okay, because we're dragging this all the way down and basically making this diode, putting this diode in reverse bias. Okay, so when that happens, D1 is going to be off. Meaning that I'm going to redraw D1 as switch. Oops. Switch that's open. And so it's going to look like R1, R2. Okay, so I redraw the circuit like that. And basically, because the switch is open, we don't see this battery or anything. This sort of whole thing is, again, out of the picture. And we end up with V out as if it's just a voltage divider. Sorry, this should be R2. And that's equal to R2 over R1 plus R2 Vn. Okay. Did everybody get there?
Yes.
Okay, awesome. So so again, it's just sort of right. This is just we aren't even using our brains here. We're just assuming Vn is minus infinite, Vn is plus infinite. So here, Vn is plus infinity. We're dragging this node so high that we're assuring that D1 is on. So this means that D1 is on. Okay, we're going to redraw as a closed switch going to the battery. And then we're going to redraw the circuit. And this time. Okay, so this is interesting. So now we shorted V out to this battery. So on one hand, we have sort of two things trying to drive V out. One of them is the battery, VD on, this guy, and the other one is Vn. Okay, now notice Vn, we have a resistor in series with Vn, okay? Whereas we're directly connected to VD on, okay? So another way to look at it is like a, I don't know, like a from here, I don't want to confuse you guys, but from maybe here to V out looks like maybe like a voltage divider, but with the resistor in series with the voltage source, which is the battery, being 0, which means that this guy, the upshot is if you have a voltage source connected to a node directly, it wins. Basically, it forces that node because it's a perfect voltage source as far as our circuit drawing is concerned. It's a perfect voltage source. There is no resistance in series between that voltage source and this node. So the voltage source, it doesn't care what Vn is, it'll always defeat Vn because Vn is going through this resistor pointing towards this node.
So V out is VD on, right?
Yeah, just V on just becomes V out. Here is just equal to VD on, regardless of what Vn does.
Does it matter if bin is like way larger than VD?
No, it doesn't
It
matter.
VD it always wins.
VD always wins because VD has, so what happens as VN gets larger and larger, it's supplying more and or trying to supply more and more current through R1, right? Say it's trying to get to this node, but this guy has just can supply infinite current into that node and will always win.
Professor,
Yeah.
so how would it look if there was a resistor after VD on?
So if there was a resistor after VD on, now you have to analyze the circuit to figure out like which one does what. So that'll start complicating the circuit quite a bit more. Okay, so you can't just assume again like this. You'll have to analyze the circuit. And like I don't know if we're gonna get there.
Professor, we will need to apply KCL at that node, right?
Yeah, exactly. Yep. You start basically applying KCL, KVL. And so you'll see, I don't think we're going to get there in this lecture, but like next lecture, we have a sort of example from the book that's quite a bit more complicated with like a bunch of diodes and resistors and stuff. So you'll start seeing cases where it's just, you know, a big mess of diodes and resistors. And there we have to, we'll end up with yet another method in like what we have to do to analyze the circuit. And that is, we just have to kind of blindly make assumptions about diodes being on or off, and then going back and checking our assumptions. So right now, we're dealing with relatively simple circuits. So we can tell when, you know, we're pulling V in very low or pulling V in very high, what we're doing to this node. Again, at those very extremes. We don't have to, you know, we can kind of just see, look, we're just a resistive divider. If I drive this thing very low, there's gonna be a resistive divider. This may not be as high as Vn, but it'll be pretty close to Vn. So if Vn is minus infinity, this guy is gonna be minus infinity times, you know, R1 over R1 plus R2 or something, whatever you wanna call it. But it just means it'll be minus infinity. Vice versa, if Vn is plus infinity, means even though I'm going through a resistive divider here, it's gonna be plus infinity. Okay, so it's easy to see what happens across the diode. But as you get the circuits more and more complicated, you're gonna start having to guess what happens with the diodes, and then going back and seeing if your guess was correct or not. Okay, so let's look at the case here now. Okay, so let's draw, since we're still here. Any questions about what I just said? Again, we're just sort of doing step by step here. This analysis of making the VN very negative or very positive, it's sort of like, that's the first thing we do. Okay, first step in the analysis. And that will do regardless of constant or ideal diodes. Okay, so let's look at this. So when okay, so let's see. So we know, I guess maybe let's do it this way. When we're very, it's easier to look at it this way. When we're very positive, so when we're very positive, V out is VD on. So that means that no matter what V in does out here, it's V out is VD1. So out here, we'll just get it like that. Okay. Now the question is, and then when we're out here, We know we got the slope over here. But then the question is, at what value of Vn do we get the break between one operating mode and the other operating mode? Okay, and so when it breaks, when, remember, in the constant voltage model, this guy, this node V out, has to equal to, so the voltage across the diode has to equal to VD on for this guy to turn on. Okay, so we know that. Okay, so for V in, to make that V out is equal to VD on, we basically plug in that number here. So V out, when V out is when, sorry. So the break point is when V out is, so break, I should have. So let me just do this. So breakpoint is when V out is equal to VD on. Does everybody see that? When V out is equal to VD on, anytime before that, or when V out is less than VD on, the diode is open. When V out is greater than VD on, the diode is shorted. Okay, but we're trying to figure out what Vn is. So we plug in, coming at the breakpoint, we basically say V out is equal to VD on is equal to R2 over R1 plus R2, we're using this equation here, times Vn, and we're solving for Vn. So Vn is R1 plus R2 over R2 VD on. Cool, so I just redraw it as 1 plus, or rewrite it, sorry. Say Vn break or something, whatever you want to call it. So here, when Vn is equal to 1 plus R1 over R2 VD on, we basically get a break in the curve. And we basically go to this guy. Okay, did everybody see what I did there? Any questions about that?
Yeah, I saw that. You know, I do have a question, because when you use the substitution method for V out, you're using it on a, I don't understand how you can use it from a different circuit, because the first one is a completely different circuit that has a voltage source versus the one where it's the diode is on and it's closed. So how are we able to do that? That's the part I don't understand.
Can you say that? I think I know what you mean, but can you ask it again?
Because you're substituting V out for VD on, but it's two different circuits. Because
so you're talking about here versus here, like which equation do we pick, or out here?
no, how can you do that? Because it's a different circuit. Because the circuit where V out is equal to R2 over R1 plus R2 Vn does not have a voltage source versus wouldn't the V outs be different because they're two completely different circuits?
Ah, okay, great. This is like a good question. So let's look at the circuit again. So trying to figure out the best way to answer that question, which is a very sensible question. But let's see. So the first thing to think is that the analysis is the same circuit. We're always analyzing this circuit. Okay.
Okay.
Now, in one case, we looked at the case where Vn is very negative. So is equal to minus infinity to some point, to the breakpoint. So from minus infinity, well, okay, sorry. So we said the input is very negative. So we looked at that and redrew another circuit, right? That was the case where the switch is open. And then we said, let's look at the case where Vn is infinite, plus infinity, and we wrote another circuit which had the switch closed now. Okay, so we redrew those type of circuits. Now, do you see how there's only one possible breakpoint in the circuit, because we only have one D1 and it's either going to be on or off. So that tells us there's only one breakpoint. Does that make sense?
Yeah, I see that.
Okay, so we can say then from Vn being minus infinite to the breakpoint, part of this slow analysis is so that I can get my thoughts together about how to answer, so don't have some patience with me. To the breakpoint, we have this circuit, and from Vn coming to the breakpoint, okay, we have this circuit, and maybe we have a single breakpoint. Okay, so we got to figure out what happens. So in this point, we know the breakpoint is right at the point where this guy turns on. So right at the point where this diode D1, its ID versus VD characteristics turns on. Right at that point is our breakpoint. Okay, and that's at VD on.
Okay. I think I'm starting to understand now.
Okay, so and then you say, okay, well, this is when this VD on is when, but that's V out is equal to VD on, it's the breakpoint. Okay, so Amber, you got that so far?
Yes, thank
Okay.
you.
Professor,
So
I'm sorry to interrupt.
Sure, go ahead.
So the breakpoint is kind of like the intersection point, right? That we find in algebra when we equate two equations to find the point at which both functions cross to each other, right? That's the way I kind of saw it in this example. Because that's pretty much the same procedure we use in algebra to find the intersecting point.
Of two curves?
Curves, lines, whatever. When we have two functions, we make them equal. We find the x, and at that specific point, they intersect to each other.
Yeah, I think that's a good way to do it. Probably that sounds good to me. I'm not Manuel. I'm kind of not very so. Once you get down the road a little bit here in your career, you kind of decide if you're mathematical or not. And I'm like not particularly mathematical the way I look at things. Okay, so I'm more like visual or by inspection. So I think if that helps you, that's a good way to go. And it's probably much more, what's the word I want to use?
Analytic method.
What's that?
The analytic method.
Yeah, the analytic method is much more robust, I guess you want to call it. Like you won't go wrong if you do that. So it's really important. Now the problem is that when you get more complicated circuits, as you'll see again in the next lecture, it's really hard to tell, like if you're just using equations. Notice we're doing something really awful here from a mathematical standpoint again, is we threw in this sort of an if-then statement here. We said, if you're up to here, you get this curve. If you're past this point, you get that curve. Here, in this example, you have 2 lines and 1 breakpoint. Okay, so yeah, you can figure out where those 2 lines will meet. Okay, but it's not gonna be always. So let me just redraw this Let me just redraw this circuit, which is also in your book, and it'll make your head hurt a little bit. We're not gonna solve it here, but like imagine if you had this problem. This is example 3.16. You had 2 diodes, a resistor, Bn was here. You had, so this is not the diodes, but a actual battery that you threw in there for the sake of sadism. And you had V out, and then you had R1. Okay, so this is something that's coming. Okay, and so this circuit has 2 breakpoints. Okay, or potentially has 2 breakpoints. You have 2 diodes that could be on or off, and so it gets a little harder to just write equations and equate them, because like you really have to kind of develop. The point I'm trying to get to is you have to get to the point where you learn how to inspect a circuit, and you just do that by doing lots of examples and using some of these approaches where you get a feeling for what's going on, and then applying those assumptions and then going back and seeing if those assumptions are correct. But when you end up with like real circuits, it gets complicated fast. And I believe the math will help you to verify your assumptions that you get through with your, so you do it by inspection. You look at it and you go, I'm going to guess this is what this thing is doing at these points. And then use the math to check whether your assumptions were correct, to double check yourself. And if the math ends up being inconsistent with your assumptions, you basically start from scratch. You go back and say, no, the assumption wasn't correct. Let me assume something else and let's see if the math is correct. But if you start with the math, you may not be able to get there because it gets really complicated. Does that make sense, man? I'm not sure if I'm explaining.
Yeah.
It's
perfect.
It's sort of it's like a dichotomy here of 2 things you have to develop. One thing you have to develop is a feel for what the circuits are doing, or a feel for analysis by inspection, quote unquote. Okay. And the tools for this feel process, the tools are things like we're exploring now, like looking at the case when the input or what something is very much negative or very much positive. So these are the kind of tools is pushing to either extreme and using these simplified diode models and stuff like that. But if that's all you use, there's a good chance that your guesses are going to be wrong because things are complicated. So that's the second part of this dichotomy, is you have to get used to using math to check whether your assumptions are consistent with the math. And so you have to kind of use both of those as things get more complicated. Okay?
Yeah.
And I think you'll, I'm hoping as you guys do more problems, like from, again, I'm going to assign the problems from chapter 3 here. Oops, we're running way over. But you'll get to know what I mean by that. So I'm sorry, guys, but any questions? I'm sorry we ran over. I got a little too excited there, but we'll come back to Amber's question, because I did want to follow this up just to kind of complete our thoughts, because it's sort of like a way of thinking. So we'll come back to start from that again. And Amber, hang on to that question, because I may have forgot exactly what you asked. And we'll start from that again, just to complete the response in the next lecture.
You know what? I think by how you drew it out, it pretty much answers my question. Actually, I wasn't seeing it, but I think I can see it now. So I'm just going to go and try and do it myself and see if I can understand it all the way.
Okay. But just do me a favor and ask it, because other people may be like wrapped around, might be confused.
Okay.
So just yeah, do me a favor, because I might forget what you were asking. So just hold on to the question.
All right.
Okay, thanks.
Thanks.
Okay, guys.
Thank you.
Have a good one.
Thank you.
Professor.
Take care.
Have a good one. Thank you.
Thank you. Have a good day.
Thank you. Professor.
Yeah.
Where can I see the homework for this module?
I haven't put it up yet. I'll put it up by tomorrow.
Oh, okay. Just want to make sure, because I didn't see it here. So.
Yeah, sorry about that.
No, it's okay. Thank you.
Okay, thanks.
Actually, Professor.
Yeah.
I don't know if you can explain this, because one thing I just didn't understand. It was the D1 on, or the voltage or the battery you put right there. Why was there a battery placed in the when you had the drawings done for this one, and in the first one you didn't put them, and this one I see that you had the batteries there.
You're talking about this one? These equations? These circuits?
So the D1s turn into like a short, but with a battery. How can you do that here? If the original equation didn't have the battery on there.
So you're okay. Let me just scroll by these circuits. I wish we were in the same room here. So you're talking about, why did I put these batteries here?
Mm-hmm.
And then compared to which?
To that one right there, the original circuit. Didn't have a battery on there.
This one?
Yeah.
So remember, this battery is actually the model of the diode. So the constant voltage diode, constant voltage model. Oops, actually, let me go all the way up. Sorry. Where were we? So in the constant voltage model, we end up putting a battery in series with the switch. And the value of the battery is VD on. So that's the diodes. That's a battery inside the diode, say, when it turns on or off.
Oh, okay. They're different models. Gotcha. The other one was ideal. diode model when that didn't have the
Yeah,
battery?
so
Okay.
the very first example, we assumed ideal diode model.
Mm-hmm.
The second, from then on, we assumed the constant voltage model. And the second one also, the third one, sorry, we also assumed the constant voltage model.
How will we know which one to assume? Would it be told to us?
I'll tell you, or the homework problems tell you.
Okay.
Yeah.
Okay, that clears it up for me. Thank you.
Okay, sure thing.
Have a good one.
Thanks, you too. Take care.
Professor, quick question.
Yeah.
Just real quick question. So the voltage of the diode is for silicon is 0.7, right? That's what we should expect in the practical point of view.
Yeah, that's what I use. I would use 0.7, 0.8, something like that. Yeah.
Okay. And for germanium one is 0.3, right? Around that, like.
Yeah,
Okay.
that's probably a good number.
Just in the practical point of view, when we solve like
Yeah.
those kind of problems, we assume that, right? Because
Yeah.
I've been watching some videos and they
Uh-huh.
use the 0.7 constant, so they just do it.
Yeah. Yeah, 0.7 is sort of like right in the middle. You can get it down to, I don't know, like 650 millivolts to, maybe 800 millivolts with like a lot of doping. Now remember that we get that.
Yeah, you mentioned that before.
Yeah. It's a natural log, not a function, but those are good assumptions. 0.7 for silicon and 0.3 for germanium is like a very good starting assumption.
Thank you, Professor. Have a good one.
You too. Take care.
All right, let's have a good one. Thank you.